All right, in this section we're going to look at the last conversation of exponential models. So just a reminder, in the prior section we looked at exponential models where they were growth of money. And we talked about compound interest. And we're just going to extend that conversation to some other applications that aren't money. So the first objective is to look at what we call the uninhibited growth model. Now, we technically could look at decay as well. So I want to point out to you here's the equation that they give us. And I just want to point out to you real quick, this is the same thing as the PERT formula, right? So we had what was it? A equals P e to the RT, right? So in the last section, we talked about continuous compounding. So in terms of money, it really wasn't very realistic to have continuously compounded interest, and there sure as hell is going to be no bank that gives you continuous interest. However, the nice thing about having that conversation about continuous compounding is it really leads us to the idea that we're talking about in this section, which is continuous growth. And if you think about, a petri dish with bacteria, right? It's continuously growing and multiplying. So this idea of continuous compounding leads very directly to continuous growth. I just want to point out to you, this is the exact same model. We're just using different letters, right? So in this model, R was the rate of interest, right? The rate at which my money grows. And in this model, we're just using the letter K. This is the rate at which my population grows or decays, right? Here, T was time, and in this model, T was time in years, right? We were always talking about the annual percentage rate. Here, T is time, but it could be any unit. It could be hours, days, weeks, months, years, decades, whatever, all right? And then here, P was the principal, which was the initial investment. And here, this is the initial value that we start with, initial population, if you will, the initial amount. So we say this A sub 0 or A naught, and this is just representing the amount at time 0, okay? Now, just to point out to you here, we could use this model for growth or decay. So if K is positive, then what we're going to get is a growing exponential. And if K is negative, we're going to get a decaying exponential. Just to remind you, we would have a horizontal asymptote here, right? So this model is going to be asymptotic, and it will decay as T goes on forever. Now, what's interesting in this textbook is he changes the letters when he talks about growth of cells, and it's because he's talking about, the number N of cells that are in a culture as time passes. Again, I just want to point out to you, it doesn't matter the letters we use here. This is the initial amount that we start with, this is my growth rate, and this is my time. Right? And then obviously, my y variables are a function of time, right? So he's calling this N of t, the number present after time t. And since k is positive, what we would have is a growth model in this case. So let's take a look at an example. So in this example, it says that a colony of bacteria grows according to the law of uninhibited growth, and the function for this model is 90 e to the 0.05 t. So N is measured in grams, and T is measured in days. All right, so part A says determine the initial amount of bacteria. Now that's really pretty easy, right? If you think about it, remember what we talked about. This is the initial amount that we start with. So for letter A, we're going to say that the initial amount of bacteria is 90. Right? Now what I did for the work was just showed you that if we're finding the initial amount, right, we're plugging 0 in for time. That's the beginning of my experiment, let's say. And remember that e to the 0 is going to be 1. So I have 90 times 1. So I start with 90 bacteria. Now again, doing this work isn't really necessary, right, because from the prior section we know this is the initial value. And then letter B says, what is the growth rate of the bacteria? So again, we know, from the last section, the growth rate here is the coefficient of the t variable, right, up in the exponent. So I'm going to just go ahead and say the rate is 5%. So we're going to grow 5% every day, right, since that's our unit. We got 5% of growth every day. Right? And then letter C says graph the function using a graphing utility, right? So whether I use my TI calculator or I use Desmos, right, here's going to be the growth model that we're going to get. And we can see right here is the initial value of 90, right? And then the function's going to grow exponentially from there. All right, now letter D says, what is the population after 5 days? So again, I'm just going to plug in t equals 5. And if I plug t equals 5 in, then I'm going to take out, whatever calculator I'm using, and I'm going to get 116 grams. Remember, n is the number of grams here. Now, 116 grams after 5 days. All right, now letter E is a different question. Letter E says, how long will it take? So we're asking for the t variable here. So how long will it take for the population to reach 140 grams? So I'm going to plug 140 grams into the y value, and I'm going to find the t that makes that happen. And this is going to become, solving an exponential equation. So remember, when I'm solving an exponential, I'm always going to isolate the exponential. So I divide the 90 over, and then now I've isolated the exponential. So the next step would be to ln both sides, right? So I'm going to ln the left-hand side, ln the right-hand side. And remember, the advantage to that in this case is that the log base e and the base e exponential are inverses. These wipe each other out, and so the exponent drops right out. So then finally, to solve for t, I'm going to divide by 0.05, and there's the time that it would take to reach 140 grams. So if I plug that in my calculator and get a decimal, it's going to be about 8.8 days. Now I want to just remind you, right, in prior sections, I think it was, 6.6, where we solved exponential equations, they always wanted the answer in an exact form. They always wanted this number, the solution, in an exact form. But because we're dealing with word problems here, it makes sense to just see what that is in a decimal approximation. So we're going to always convert to decimal approximations here and tell us, the days or hours or whatever the time unit is. Right, and then letter F says, what is the doubling time? Right, so if I've started with 90, then I double to 180. And again, I'm finding the time that makes that happen. So this is identical to what we just did in letter E as far as our process is concerned. So I have to isolate the exponential. So I'm going to divide both sides by 90. And then I have to, log both sides of the equation. So if I log the left-hand side, log the right-hand side, that log base e and the base e exponential are inverses. They undo each other. I get just the exponent there. I'm going to divide both sides by 0.05, and there's the time it would take for us to reach double the amount. And again, I plug into some calculator and get a decimal of 13.9 days. All right, and again, I want to remind you for both of these, especially letter E and letter D, you want to check your work, right? So a couple different ways to check your work. Again, I could take t equals 8.8 and I could plug it back in here and use my calculator and see what value I get. Right? I could plug in 13.9 back into my calculator and see what value that I get. Right? Or I could graph as well. All right, so just for illustration here, I brought up Desmos and I typed in y equals 90e to the 0.05x. Right? Remember, that is my equation, 90e to the 0.05t. But I'm going to use y's and x's in my calculators, right? And let's check this one. So I want the y value to be 180, and I know that's going to be about 13.9 days. So I'm going to graph y equals 180 on my calculator. So let me hit enter, and I'm going to graph y equals 180, and I'm going to find where the population is 180, and I can see there's my 13. Come back. There's my intersection. Right? I can see 13.9 days approximately is that intersection point. All right, let's take a look at another example. Now, in this example, we're going to make it a little bit more difficult, and we're not going to have the equation to start with. So notice in the prior example, they gave us the equation, 90e to the 0.05t. But in this example, they're not giving the equation to us. All right, so we are told that the number of bacteria doubles in 4 hours. Right, and we know that this is growth, right? So we have bacteria that's growing inside of a petri dish, right? So if we start with the equation of growth, right? So we have our initial amount and then e to the growth rate times t. And notice I've even switched letters around here, right? So instead of using the letter K, I've used the letter R. Again, it doesn't really matter what letter that I use, just know that this is my growth rate. So if I plug in the information that I know here, I know the number of bacteria doubles in 4 hours. So even though I don't know how much bacteria I have officially started with, I know that it will double when time has passed 4 hours. So whatever my initial population is, I'm going to have twice that value when time is 4 hours. And I can just solve this equation for R and find that growth rate. So I'll divide both sides by n sub 0. And then I'm going to ln both sides of the equation. Remember, I'm going to take the ln of the left side and get ln of 2. And when I ln the right side, it undoes the e, and I'll just get the 4r that drops out of that. Then when I solve for r, divide by 4. So here's my growth rate. Now I could get a decimal for that if I wanted to. Typically, the best thing is to leave it in an exact form so that we're not introducing rounded values into my equation. Right? We typically don't want to round until the very, very end. Okay, so we're going to leave the growth rate in a exact form. So there's my equation, right? So that's letter A. Letter A said find the equation as a function of time, right? So there's my equation. We had to find the growth rate, knowing that the population doubles in 4 hours. Now letter B says how long will it take for the size of the colony to triple? So now that I have the equation, that'll be an easy question to answer. So whatever my initial value is, it's going to triple, and then I'm going to solve the time that it takes for that to happen. So again, I'm going to divide both sides by this coefficient to isolate the exponential, and then I'll ln both sides of the equation. Now again, remember, I really could kind of skip this step here because I know when I ln the e, that's going to undo each other, and I'm just going to get the exponent out of that. Right? So I end up at that point, right? And then I'm solving for t, so I'm going to multiply by 4 to get rid of this 1/4, and then I'm going to divide by the ln of 2, and there's my time. Now it's okay to round. Right? So now I'm going to finally round and get approximately 6.34 hours for my population to triple. All right, now let's suppose that I wanted to graph and check my work. Right? So keep in mind that in this equation I found, I don't know the initial value, and it really doesn't matter the initial value. Whatever I pick, I would have doubled it over here, right? Whatever I had picked, I would have tripled it over here, right? So for my calculator, right, or Desmos, I just let the coefficient be 1. So you can see here's my initial value of 1, right? So again, to check my work, let's say on letter B, I'm going to plug in, if this is 1, then this is 3 times 1, which is 3. So I'm going to check when I would reach triple the initial amount, and I would just graph y equals 3, and I would see there's that intersection point of 6.34 that we got from our by hand work. All right, let's take an example where we will look at what we call the law of decay. So again, here's the formal equation. I mean, we've talked about this already, right? This is the same equation as the growth equation. The only distinction is our rate of growth is now a rate of decay because it's negative, and that's going to be a decreasing exponential graph. So in this example, we talk about strontium-90 is a radioactive material that decays according to the function a sub 0 e to the negative 0.0244 t, where a sub 0 is the initial amount present, and a is the amount present at time t. This time t is in years. Assume that a scientist has an initial sample of 800 grams of strontium-90. Letter A says, what is the decay rate of strontium-90? So again, in our equation, right, this is the decay rate. So we know it's decay because it's negative, and the rate is 0.0244. So we'd write that as a percentage. Say the decay rate is 2.44%. Letter B says how much strontium-90 is left after 30 years. So again, similar to what we did in the prior problem, we're plugging in 30 for the time. So we're going to just plug into the equation, take out our calculator, and give that value. So we have, in this case, 384.76 grams. All right, so let's take a look at letter C then. Letter C says, when will only 600 grams of strontium-90 be left? So again, just like in our last example, now we're asking the question of when. That's solving for the t variable. So we're going to set the function value to 600. We're going to isolate the exponential. We're going to divide the 800 over. Then we're going to ln both sides. I'm going to start to get a little bit lazy here. And when I ln both sides, I'm going to remind myself ln of base e are inverses. They're going to undo each other. I'm going to just get the exponent to drop out of that. And then I divide both sides by the 0.0244, and there's the time. So we'd say about 11.8 years for there to be 600 grams left. And then letter D says, what is the half-life of strontium? All right, so half-life is the time that it would take to have half of our initial amount. So if 800 is our initial amount, then we're looking for where our value left is 400. And then again, just like with letter C, I'm going to solve for the time variable. So I'm going to divide both sides by 800, then I'm going to ln both sides, and then I'm going to divide by the coefficient of t, and there's our approximated value of 28.4 years to be the half-life. And again, whenever you're doing these problems, where you're solving for time, I would always recommend check your work, right? Again, multiple ways to check your work here. I could take 11.8, I could plug it back in for the time variable, take out my calculator, crunch that number, and see that I get 600. And then ditto, take 28.4, plug it into my time variable, crunch this in my calculator to see that I get 400, right? Or I could do the graphing approach like I showed you earlier. All right, and the next example, similar to what we just looked at, says traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. All right, so it's known that carbon-14 is a radioactive element that decays. It's an unstable element, and the radioactive is, it's not going to kill you, okay? But it's an element that is unstable and decays, and it's in all living items. So we know, it's pretty well known that the half-life of carbon-14 is 5,600 years. So it says approximately when was the tree cut? So again, in this example, I want to point out to you, we're not given the equation of decay like we were in the last example. But we are given information where we can find the decay rate. So again, if I start with the equation, typical exponential model, I know that the K value here is going to be negative if this is a decay model. And I'm being told that the half-life is 5,600 years. So whatever amount I start with, I'm going to have half of that left when T is 5,600 years. So I could pick a number here. I could pick 500 and this would be 250, right? I could pick 1,000, this would be 500. I could pick 1 and this is a half, right? So plugging in the time of 5,600, right, I can find my decay rate. So again, I'm going to ln both sides of this equation. I'm going to get ln of 1/2 on the left, ln of the base e exponential. Those are inverses. They undo each other. I get the exponent drop right out, and then I'm going to divide the 5,600 over. Again, I'm going to caution you here like we did 2 examples ago, right? Once I find my K value, this is like an intermediate step, okay? So I'm plugging the K value into my equation here. I don't want to round that K value. If I round this K value and get a decimal approximation, I'm introducing rounding error into my problem. So unless my math lab says round the decay rate, to 3 decimal points, I don't want to. I want to keep it exact. Now, to finish this one off, it says approximately when was the tree cut and burned. So when it was found, it had 1.67% of the original amount. So I'm going to take my original amount, I'm going to multiply by 0.0167 because that's 1.67%. And I'm going to solve that equation for T. And then again, this is getting kind of repetitive, right? You're going to get really good at solving these exponential equations. Because now I'm going to divide both sides by a sub 0, and then I'm going to ln both sides of this equation, That's going to undo the exponential over here. I'm just going to get the exponent drop out of that. And then I'm going to multiply both sides by 5600 and divide by ln of a half. And there's the t value that we would get. So it was about 33,000 years ago when the tree was cut and burnt, so that now we have found it with 1.67% of the initial amount of carbon-14. All right, the third objective in this section is to use what's called Newton's law of cooling. Now here's the equation for Newton's law of cooling, and just to point out to you here, they're changing the letters on us, but let's talk about what these letters mean. All right, this is the temperature at time t. This capital T represents the temperature of the surroundings. So T is a constant temperature of the surrounding medium. I mean, usually that's the air temperature that my object sits in. I guess it could be water or whatever, medium I'm putting my heated object into. I mean, typically, let's say we have a cup of coffee that we've heated and we've set it on the table. And so cap T is the temperature of the air around the heated object. And then U sub 0 is the initial heated temperature. Now in this case, K is going to be a negative value because we're going to have decay. Right? So if we have heated an object, it's going to cool and the temperature will decay. So maybe as a quick example, right? Let's suppose, kind of that cup of coffee example, right? Let's suppose we heated a cup of coffee to 100 degrees. So my initial value is 100 degrees. And then the temperature of the air in my office is 72 degrees, let's say. So I'm plugging in the temperature of the surrounding air. And let's suppose we know that in this situation, the decay rate is negative 0.3. Okay, so decay is at 30% per minute, let's say. So if I plug this into Desmos and graph it, right, just to visualize the scenario, I just wanted to point out to you, right, here's my initial temperature, and notice my exponential is going to decay, and it's going to approach, this is the room temperature of 72, right, so it's going to approach the temperature of the surroundings. A cup of heated tea or coffee is going to cool down to the room temperature. So that's what this model is representing here. When my K value is negative, I get decay down to this asymptotic behavior of approaching the room temperature. So let's take a look at one example of Newton's law of cooling. So in this example, it says an object is heated to 100 degrees Celsius and then allowed to cool in a room whose air temperature is 30 degrees Celsius. Now, if you remember, 100 degrees Celsius is boiling temperature, so that's really, really hot. Right? That's 212 degrees Fahrenheit. So our object is heated really hot. Right? So it says, if the temperature of the object is 80 degrees after 5 minutes, when will its temperature be 50? Now, in my prior example, I got the answer down here and it's showing, and it's not supposed to be. I just noticed that, right? Whatever. So in my prior example, I gave you the equation, right? Just to point out to you, here's the equation. I gave it to you, all right? In this example, we don't have the equation. So we're going to have to do just like we did in some of the other examples. We're going to have to find that decay rate. Now we're told that the temperature of the object is 80 degrees after 5 minutes. That's going to help us find that decay rate. So let's first plug in what we know. We know the object was heated to 100 degrees, and we know the temperature of the surroundings is 30. So we know the object was heated to 100 degrees. We know the temperature of the surroundings is 30. So we plug that in. Right? So obviously this is going to be 70 here. And then I need to find my decay rate, right? My temperature decay. So I know that after 5 minutes, when T is 5 minutes, the temperature is 80 degrees Celsius. So if I plug that in, then I should now find K. So again, here we are solving an exponential equation. First thing I'm going to do is subtract the 30 over, and then I'm going to divide by the 70. So 80 minus 30 gives me 50, and then I'm going to divide by the 70 coefficient. Now I'll ln both sides, and then I'll divide the 5 over, and there's my decay rate. Now again, I want to keep this in an exact form, so I'm going to plug it up in here to my K value. So there's my K value. Now the second part of the question says, when will its temperature be 50? So I'm going to plug 50 into the temperature, and I'm going to solve for T. So again, now plug 50 in, I'm going to subtract the 30 over, that's going to give me 20. and then I'm going to divide by 70. Then I'm going to ln both sides. The e and the ln are going to undo each other. And then I'm going to multiply by 5 and then divide by this ln, and that's going to give me my t value. Plug that into the calculator, and that's about 18.6 minutes. All right, now I'm going to take out my graphing calculator and check my work here. All right, so using Desmos, right, I plugged in my equation here, and notice, here's my initial value, and then here's my room temperature of 30. We can see the temperature decaying down to the room temperature. So I want to check the temperature being 50, giving me about 18.6 minutes. So I want the temperature to be 50 degrees. So I'm going to graph y equals 50, and I'm going to find that intersection point. I can see there's my 18.6 degrees, and we're checking the work that we have here. All right, now the last objective in this section is to use what we call a logistic model. Now here's the idea behind a logistic model. In the very beginning of the section, we used exponential growth. So we had an initial value that we started with. We called it like a sub 0. And we talked about the population growing exponentially. Okay. Now, a couple things to talk about here as far as realism. And we're talking about, most things. Let's look at humans for a moment, right? So humans are, overpopulating this planet. There's not a lot of things that kill us off and control our growth. Now, in our history, there have been some things that have controlled our growth, like the Black Plague. We've had diseases, sometimes war or famine controls our growth, slows us down. But for the most part, we have what is called uninhibited growth. And that was what we looked at the beginning. Now, the reality is not all things on this planet or all things in life grow in an uninhibited fashion. So, for example, let's suppose we have, let's say, rabbits in Arizona. Right, so we have rabbits that we're looking at in Arizona. Definitely if I place some rabbits in Arizona, right, they're going to start to grow exponentially. But there's foxes that live in Arizona, and I know this is kind of sad, right, but the foxes have to live and they're going to eat the rabbits. There's going to be limitations to the growth of the rabbits. There's also going to be food limitations and things of that nature. So there's going to be some point where the plateau of the population, the population is going to reach some kind of limiting amount, right? Like a horizontal asymptote here. So we're going to reach some level where the population kind of plateaus, and this is what we're going to call a logistics model. Now here's the equation of a logistics model. It looks something like this, right? So the letter C, the letter A, and the letter B are all numerical values. C is what we call the carrying capacity. So what, the plateau that we talked about on that prior slide. We'll see that again in a second, right? So if we were to look at, and then again, hey, before I change the slide, right? B is my growth rate or my decay rate, right? So if I look at this idea here, so if B is positive, we're going to get what we call growth. So C is my carrying capacity. It's the plateau of my population, right? And here's my initial population. So my population grows exponentially at first, but then it plateaus, right? If this B value here is negative, I'm going to get decay. So I'm going to have an initial value, and then it's going to decay down to 0. Now, in particular, let's look at this model real quick. What you're going to notice is that this term right here, this exponential, as time goes on forever and ever and ever, this exponential term gets smaller and smaller and smaller and goes to 0. If I had e to the negative infinity, if that was possible, right? As time goes to infinity, e to the negative infinity goes to 0, gets smaller and smaller and smaller. So as time goes on, this term diminishes, and I get c over 1 in the long term, right? So as t goes forever and ever and ever, the function approaches this carrying capacity because this exponential will diminish over time. So let's take a look at one example here. It says that fruit flies are placed in a half-pint milk bottle with a banana for food and yeast to stimulate laying eggs. Suppose that the fruit fly population obeys this logistic model. And the reason that this fruit fly is going to obey a logistic model is because we've put them in a half-pint milk bottle. So there's only so much room for them to grow. And at some point, there's a limitation to their growth. All right, so we're using a logistic growth model here. We can see from this model, here's my carrying capacity. So we've predicted that we're going to have 230 fruit flies in our model. And we can see here's our decay rate. Our decay rate is going to be about 37%. So letter A says state the carrying capacity and the growth rate. And again, we can see those right from the model. So state the carrying capacity and the growth rate. We can see that as time goes to infinity, right, the exponential is going to get smaller and smaller to 0. So our carrying capacity is that 230. And then the growth rate is that 37% that we talked about. Now, letter B says determine the initial population. Again, just like in all of our prior models, the initial population comes from plugging in 0 for time. So if I plug in 0 for time, remember that e to the 0 is 1. So I'm going to get 56.5 times 1. So I get 1 plus 56.5 in the denominator, and I'm going to get a value of 4. So we're going to say the initial population was 4 fruit flies in that half-pint bottle. And letter C says after 5 days, the number of fruit flies in the half-pint would be, and we're going to plug in 5 to find the population after 5 days. So if I plug 5 in, take out my calculator, I'm going to get about 23 fruit flies after 5 days. And letter D said, when will the population be 180 fruit flies? So I'm going to set the population equal to 180 and solve for T. And this is a little trickier than some of the prior ones, but no big deal, we can handle this. We have a fraction. So remember, I need to isolate this exponential. So the first thing I'm going to do is get rid of the fraction. I'm going to multiply this denominator to the right-hand side, and that way I just get rid of the division. Right? And then the next step would be to divide the 180 off. So I'm going to divide the 180 over. Right? And then as I continue to isolate this exponential, I'm going to subtract the 1, and then I'm going to divide by the 56.5. So finally, I isolated the exponential. I'm going to ln both sides of this equation. And again, lning the e undoes that, and I get just the exponent. And so the value that we get, right, if I divide by negative 0.37, I'm going to get about 14.4 days to reach the value of 180. All right, so then to answer the next one, this was the last question. How long does it take for the population to reach 1/2 of the carrying capacity? So again, we know the carrying capacity is 230, so 1/2 of that is going to be 115. So I went ahead and took out my calculator to do this work, and I graphed the equation that we were given. Here's the equation. I graphed the carrying capacity of 115, and I got approximately 10.9 days for that to occur. And then I did this on Desmos as well. Here's my exponential model. Here's my carrying capacity of 230. I went ahead and graphed y equals 115, and I could see that intersection point of about 10.9 days. All right, so that's everything we wanted to cover in 6.8, applications of exponential models. As always, if you have any questions, please post on the discussion board.